Okay, great. So can everyone can see the screen share too? There's no problem. Okay, so chapter 7, we're almost at the end of part 1 on these so-called tabular methods, where we have a problem where we can enumerate like all of the state action pairs in the problem. So these trajectories through the environment of this state, I mean, really like this, the states, but the actions themselves too. We can sort of try to estimate the value of each state. And the problem's small enough that we can have a distinct value for each state. In part 2, we'll get into more approximation methods, which require other techniques. But this is sort of the last generalization of these tabular methods. And what we had started out with the Monte Carlo methods, and the Monte Carlo methods, I have a diagram here, involve this sort of trajectory where we take the trajectory to some terminal state, and then we use all of the information along the trajectory to calculate the state value estimates or the state action value estimates. And then, after that, we looked at this opposite extreme of temporal difference learning, where I have the diagram here. Okay, sorry, just trying to find the backup diagram, where we had just looked at sort of a single forward transition. And then this method involves bootstrapping, where because we only have one transition to look at, we don't have the information about all the future returns, but we do have this existing estimate for whatever state we end up in, and then that estimate can be used to update the other estimate. So what this chapter is concerned with is sort of everything in between those two extremes. So n-step bootstrapping, as opposed to, so the one-step version of this is equivalent to the temporal difference learning we were looking at in chapter 6.
And then putting it as infinite, then it would be essentially Monte Carlo method, because you would have to run through the end of the episode, essentially.
Yeah, so if n is infinity, then we'll see that is equivalent to Monte Carlo methods. And I will also say that the algorithms in this chapter, you probably, even though they do generalize the previous 2 sections, you probably would never use the methods in this chapter, because later on there's this method of eligibility traces, which ends up sort of subsuming these methods and does the calculation more efficiently, but it's a little more obscure to sort of learn about. So this is the purpose of this chapter, sort of to introduce the concept of having some n, where n is some arbitrary value. It doesn't necessarily have to be 1 or infinity. So it's good for introducing it, but it already mentions in the introduction here that really the stuff in chapter 12 is really what you would end up using if you wanted to use a method like this. So, all the sort of math and algorithm details in this aren't really that important to go through, but we will look at the implications of different n-step methods and how they work. So this backup diagram kind of shows the summary of the spectrum, where we had the TD0 method in previous chapter. We had Monte Carlo in chapter 5, and the backup diagram showed this whole spectrum in between. So the idea is that whatever the number of steps is, you have this formula where you sample the returns along the trajectory, and then at some point, you're going to stop looking at the rewards, and you're going to instead use the value estimate here. So for Monte Carlo, this point would only be at the terminal state. And actually, there wouldn't even be a value estimate, because the value at the terminal state is always defined to be exactly 0. So if whatever n we're looking forward is less than the terminal state, then we actually have to use the value estimate at that time step in the future. So does this make sense to people for how the return is calculated? Whereas this is the return used for the Monte Carlo return, where we go all the way to termination.
Yeah, that makes sense, with, the goal, with the reward state being, the summation of the reward with gamma discount, which would eventually make, the discount very small. And then, the difference between one step return just having one value iteration, and then the two-step return basically having it only after the second step. Yeah, that makes sense.
And this is, the n step formula, then we have this in general, this goes out to n, and for sort of notation convenience in this chapter, we define the n step return, because normally, the return g sub t is the discounted sum determination. But to make it, more compact to write things, we have this alternative notation for g, where instead of going to termination, we go to the step t plus n, whatever that is. And, because we're sort of cutting off the return here, this does also include the bootstrap value. So, this value, like the expected value of this, should be the same as this expected value, because, as long as the value estimates are being computed correctly. And then, this update rule for estimating V is the same structure as before, except, here we have a different target, and the target is just going to be the n step return, as opposed to the return determination. Yes. Here, yeah. If anyone, there aren't that many people here, so if anyone has a question, you can just, feel free to say it. Like,
Jason, so I'm a little bit confused. I thought for reinforced learning is that we're trying to, right? It's a mix of labeling and like supervised and unsupervised learning, right? You're training the agent to learn.
I should be clear here that what is so far in this chapter, we are just looking at the case of estimation right now. So there's no training going on. So this would be the update rule to calculate the value estimates under a given policy.
Okay.
So, right, this return, this G, right, is computed from some trajectory where the agent is taking actions, which is resulting in these reward values.
And the t plus 1 is basically how many times, right? Like you say, you were talking about temporal. So it's the first trial, the second trial, the third trial.
No, these are not trials. So these are the steps in the trajectory. So if you imagine this diagram here, like these open white circles would be the states, the black circles are the actions. So this is like from the starting point of the environment, the agent will make a series of steps like this.
Yes.
And then this is like the 0th step. And then you look into the future for both, what state you end up in and what the reward values are along the way.
Right.
So this whole thing, this formula would be for a single trajectory.
So your two-step would be, right? The first one would be t plus 1. Second one would be t plus 2. Where this three-step would be t plus 1, t plus 2, t plus 3. Is that correct?
Yeah. Whatever the n is where, here, this equation summarizes that. So you go up to n for the reward, and then whatever state you end up in, you use the existing value estimate for that state.
Thank you.
And this would be the simplest case of this is just the one-step return here, where there's just a single step into the future. Now it's just, we're generalizing it, so there's, but and each one has to be discounted by the appropriate, power of gamma. So then, as before, this is sort of the averaging style update for the value estimate, where we have some constant step size here. I mean, really what we're doing is we're updating the value estimate with these, by averaging these G values, and this difference here is how much of an update we're making to the value estimate. But this update rule is exactly the same as what we had before. It's just that the target is different, where now it's the n step return instead of, if this was G sub t instead, then this would be, the Monte Carlo update rule. Yeah, so then there's this point about the previous chapter, how in order to prove, like most of the proofs about these update rules and whether or not they converge depend on the value estimates we have at a given time step are based on the value estimates at a previous time step, but we don't actually, we have to, for the purpose of proving things, assume that the value estimates don't change like during a particular episode which is running. And in this algorithm, you can see here that we just update the value estimates as they appear. And if we visit a value more than once in the episode, like we're performing these updates in the middle of the episode. But there's this question about if there's a static method here where we maintain sort of two copies of the value estimate. So when we're doing this update, we could like have the previous value estimate saved and static and unchanged. Then we run through an episode, perform all the updates, have new value estimates based on the old ones, and then we can, replace the old ones after we're completely done with that. And I did it here where, so you can sort of run this experiment. This is this exercise 7.2. And what do they ask? They ask you to devise a small experiment. So I did this experiment, which is just, it comes up in a later example, but if you recall from chapter 6, I think we had this random walk example where we just have a chain and the agent, bounces back and forth along this chain. And in this, for this problem, the value estimates represented by this black line, where it's just this linear, it just value, it just varies smoothly from these values that are proportional to the length of the chain. So the value here is like, should be 1/6 for a 5-length chain. So like 1 over n plus 1 and then 2 over n plus 1. So this graph, this is for a longer chain. So this is like a 19-state chain, but you can, vary this and look at it for different length chains. And because I know what the true values are, this is showing what the error is while this is calculating the value estimates. So this is the error for different values of alpha and over, pretty early on in the training process. So just for the first 10 episodes. And it appears as though the normal version, like the version in this pseudocode, where we just update the values, we just have a single set of value estimates, appears to be more efficient than the static version, which is this orange curve, where we actually maintain 2 copies. So I have the, okay, well, I wrote it all in the same function here, but there's this static values flag, and if the static values flag is true, then there's a copy of the values which is saved. And the update value is calculated, and only the copy is updated in a single episode. And then only when the episode is completely finished do we replace the values with the copies. So, that's the difference with the static method. And the point of the dynamic method being faster is just that you're using the updated information as soon as you have it. So you could believe maybe that it would converge faster. And in practice, it does seem to converge faster if you just don't worry about keeping a separate copy.
So
So
Jason, I'm sorry, can you explain this graph? So you have the blue one is a non-static state. What does that mean? That means it's not moving. Your chain is not moving. And your red one, or wait, what? That doesn't even make sense. Non-static means it is moving, right? Static state means it's not moving. Is that correct?
I mean, static means that, so non-static is the normal, if you look at this pseudocode here, there's just one version of V. So
And V
during an
for value,
episode, the
right? V
state
for,
values,
okay.
yeah. So the state values will be updated as soon as, for every time step T here in an episode, the state values are updated. So if we visit a state more than once, the update we're going to use this target where we're looking at the previous value is now going to be the updated value, like within that episode. In the static version, you have so before the episode starts, you have V, and it's like you call it V static. And then during the episode, you calculate these updates. But here, like this part of the update where you have the target here, the target would use the static version of V, which hasn't been updated yet during this episode. So it's not a big, like it all converges to the same thing. The question is just which version is more efficient. And the version in the book, in most cases, will be more efficient because you're updating V as soon as possible instead of, waiting for the end of the episode before you actually, implement any of the updates. So it has nothing to do with the MDP or the environment or anything. It's just whether we have one or two copies of the value estimates.
Right, but how are you defining efficiency? Is it that the blue?
Oh, here, well, the error is, so it's learning faster, basically.
Right.
So it's converging faster to the true values. Because here, the curve here is the error on this task.
So the y-axis is your error, is that it? Or
Yeah, because this is a very simple case, this chain, and the true values are represented by this black line here. So
okay.
as we run episodes, the estimates get updated and converge towards the true values. I mean, there's also, this is also showing the optimal learning rate here, which is, but you can see across a range of learning rates,
Yes.
the dynamic method is faster.
Thank you.
It's reaching a lower error faster. So yeah, this is just, we already talked about this in the previous chapters but just practically you don't have to, you don't have to keep two copies of the value estimates. Okay, so now for the first major example for the n-step methods, we're gonna revisit this chain, which is the one I showed here. So just, to remind you, I can show this running. So this thing, the actions don't matter. At every step in this chain, the agent will either step right or left with an equally random probability. And if you exit to the right, you get a reward of 1. If you exit to the left, you get a reward of 0. And this ends up producing these value estimates, which are represented on this black line. And if you make the chain longer, if I go up to 10, these value estimates continue to, like the slope of the line changes, but it's always 1 over n plus 1 for the first value estimate in the chain. So this was showing for TD0 methods how this works. But the question now is, if we're going to apply the n-step learning to this, we can make the same sort of graph where we look at the error after a certain number of episodes. And if the error is, now, of course, all these methods will converge after an infinite number of time steps. But here the question that is being considered is which method is converging fastest. And this doesn't tell you completely which method converges fastest, but at least, after 10 episodes, like if we only had 10 episodes available to train, apparently for this here they've made the chain 19, a 19 state chain. So here the n equals 4 method appears to converge the fastest, at least as long as you use this particular learning rate of alpha. Of course, like this is also in retrospect, like if you compute all of these, then in retrospect, you can see which method is better. But as a demonstration, it's just showing that depending on the size of the problem, there could be a particular value of n which is optimal or which learns the fastest. And if we go to here, so I have a similar thing here. Oh, they've also modified this chain so the reward is -1 at one end and 1 at the other end, and it just changes the problem slightly so that the mean reward is 0. And that's why this problem was initialized. All the state values were initialized at 0 for this, because that is the middle value. So this n equals 4. Now there is a question here, which is compared. So in the previous chapter, remember this random walk, the example had only 5 states in it, and now suddenly they're doing it with 19 states. And for the 5-state problem, that's where it was showing how the advantage of TD0 learning over Monte Carlo learning in the case of the chain. Now, here they're sort of showing how the n equals 1 is worse than some of these higher n's, but we're using a 19-state chain. And the question is, why do you think, the larger n here was used for this example? Like, if they try to do the example with the 5-state chain from chapter 6, would the same point be made? So I can show you in a second what the result of that is, but does anyone have a guess or thinking about why, to make this point, a longer chain is being used, or one with more states?
You would just think that the lower the state, like if you have 5 states, the error should be less, right? Where the more states you have, you should have more error. No?
More. Well, here we're comparing the different methods. So whether the error is higher or lower overall, the question is which value of n is the most efficient.
Well, based on the 19th state, you said n equals 4 is the most efficient, right?
Mm-hmm.
So but your state and n are not the same. So if you say state of 5, you're talking about 5 states, not n equals 5, right?
Yep, that's right. Mm-hmm. Yeah, but the question is, if the states were much smaller, like 5, would a different value of n be more efficient than a larger value of n?
no idea. We need to see more data.
Yeah, well, you can generate the data and look, but this is more about intuition about the problem, because we have the extremes. Actually, if we go back to chapter 6, so this is comparing the Monte Carlo to TD0, and for the small, well, here I'll go back. I'll make this for the 5-state chain. One of the points was that the TD methods are much better than Monte Carlo, right? And there was some intuition about that with sort of the advantage of bootstrapping in this case. And there was also an exercise showing a method of computing the values where you can set up this set of recursive, or you can set up the system of equations on the states to compute the value of each state. And this algebraic setup is similar to TD0 because the equations themselves are bootstrapping on the neighboring states. And if the chain is sufficiently small like this, the system of equations can be easily solved. And that was part of the intuition of why the TD method is better than Monte Carlo, where each estimate is just, you have to average out to infinity. So now we have this 19-state chain, and while so Monte Carlo here would be these lines, like where you're getting very high ends as n gets arbitrarily high. You can see here Monte Carlo was also pretty bad, but we still have, an n slightly larger than 1 is still optimal here for the 19-state chain. So yeah, the question is if anyone has any intuition on whether, how the optimal n changes with the size of the chain. But I mean, it's fine if no one has any intuition about it, because we can just look at how the answer varies with the chain length. But let's see, as an example, I can set the chain back to 5, which was what it was in chapter 6. So let's see. So this is the 5-state chain, and it looks like the best value of n is actually 1, which is the TD0 method we had from chapter 6. Okay, so I mean, if the point of this chapter is to show the advantage of n-step methods, obviously a 5-state chain would not be a good example, because all we've shown is that n equals 1 is the best. So why bother going to 2 or 3? But it depends on the problem. So obviously you can use this chain as sort of a mental model of different types of problems, but as the chain gets longer, you can see at which point. So when there's about 9 or 10 states, the optimal value is 2. And then as we keep going up, so what's happening is as the chain gets longer and longer, the optimal value of n is going to shift higher. I can see how. Let's see if we go up to like 35. Let's see what it'll take a little longer to converge. But already for this, yeah, so for 35, it looks like even an n of 8 or 16 or 8 is probably the best for this. So as the chain is getting longer and longer, the Monte Carlo, we're getting closer to the Monte Carlo method.
So is it correct to say then that the n is approximately 20% of the chain length?
I don't know. Is that what's happening? I mean, we can see, I mean, I guess one way to see is I'll make it a much larger value, like 75. We can see. I hope it doesn't take too long to run. The episodes themselves are going to get much longer as well as the chain gets longer because it just takes, you know, that much longer to exit the chain. Actually, it should be growing, I think, quadratically with the length of the chain. So we can wait and see how long it takes to run. But yeah, so I mean, whatever the reason is, clearly as the chain gets longer, okay, so this finished. So now at 75, now it's n equals 32. Appears to be the best. I don't know. Does that coincide with your estimate of the relationship?
No, it's approximately double the value I estimated. So 40% of the chain?
Okay, but remember, like before I had, with the length of 5, it was 1. And then 19 was 4 again. So I don't know. There may not be, I mean, it probably, it does certainly depend on the expected number of steps before exiting the chain, which I believe should just be growing quadratically with the length of the chain. If I had it in here, because it's basically just like this, like heat. It's almost like it's also a model for like heat diffusing in a system, or just a random walk, how quickly it spreads out. But yeah, but does that make, so obviously, do people understand why it's like, to make this point about n-step learning in the book, they have chosen a longer chain example because you have to use something larger than 5 before you start to see the larger values of n play a role or be more optimal.
Yes, I understand this now.
Yeah. And I think there was, so also the state values were initialized at 0. And you know that for this chain problem, the way it's set up here, 0 is the best initial value because it's correct for the center state, and then the error is symmetrical on either end. Like that, if you're going to pick a single starting value, that value minimizes the error across the whole chain. And remember that the n-step methods make use of the other value estimates. So if you were to start with a really bad initial, like here, I'll go back to the 5-state chain where n equals 1 is the best. If you have a really bad initial value, then what do you think that will do to the value of n? Or will it, affect anything at all?
I'm sorry, ask again. What is a bad value for, what would consider to be a bad value?
Well, 0 is the best value.
Right. So a
Initial
bad value
value.
could be a 0 or 1 then. Is that what you're saying?
Well, anything other than 0 will be a worse value.
Oh.
Initial value. I mean, we have some starting error. In this case, I'm initializing all the value estimates at the same value. So there's a particular value which minimizes the error. Now, obviously, the error is minimized when the values are all correct, but for the initial value, they all share the same value. So 0 is the best single starting value. If I change it from 0, it means that the initial value estimates are going to be, on average, more wrong from the true values starting out. So the information contained in the value estimates from the start will be worse if I change this from 0. And the question is, how will that affect, which, or will it affect at all which n is best?
So just to visualize this process, instead of speaking theoretically, Jason, what you talked about is that, for example, if we're walking, this is a random walk. If you turn right or if you turn left, then you skew from 0. Is that correct?
So that in this case, what the 0, so here, this is shifted up, but imagine it's all shifted down 0.5. So here, this horizontal line here, if this black line is the true values of each state, you can see that if we initialize right here, then this is right in the middle. Like if we were to initialize up here or something, there'd be a much larger starting error than if we initialize right in the middle of the true values. So here, like the values are just the value of each state. Like in this random walk, the reason why the values are larger to the right is because to the right, we're closer to exiting on the right, which has a reward of 1. So that's what creates the values in the chain, is the difference in reward exiting to the right and to the left being different. But here, so let's just try this out. So I'll change this initial value from 0, let's say to 1. Okay, so it seems to have dramatically changed. So now n equals 2 is better. And let's say I make this like a 10. Well, in addition to the whole problem being, not converging well within 10, or yeah, over the first 10 episodes, or maybe 10 is too extreme. Change it to like a 2. So you could see that what this is doing, having this worse initial state value, is it's making the n equals 1 method appear to be really bad. And this should make sense, because if n equals 1, this method makes the most use of the other value estimates, right? If we go back to this formula, right? If n equals 1, we have 1 reward, and then we have the value here, right? The larger n, the more rewards we're including in our estimate of the return. And we're also, discounting further the value estimate into the future. So if your initial values are really, really awful, then a method that's getting closer to Monte Carlo is probably going to be better, because it's just going to completely ignore whatever the initial values are from the start. So that's another factor that can affect which n-step method is best. So it's both like the nature of the problem, in terms of like how far away are you at any given time from the goal, or from the terminal state, and also how off are your initial values. So like in this problem, we know which initial value is good, because it's a contrived problem. Like we know what the true values are. But there could be other problems where you initialize the state value function like at 0, because it's just, why not make it 0? And it may not be obvious from the problem, like you don't know what the true values are, right? That's the whole reason why you're applying one of these techniques, is to find the value function. So you don't necessarily know ahead of time that the value you're picking is like the best initial starting value. So obviously we would always like to pick a good initial starting value, but if we can't, just know that like that could conceptually, that could definitely affect, which method actually works the best. But is that like, but the basic like overview reason is that the smaller the value of n in this technique, the less the technique depends upon the existing value estimates, and the more it depends on the sampled rewards. So if we have less faith in our initial value estimates, a larger n will produce better results. Is that any questions about that?
But that makes sense, right? In an experiment, the more trials that you run, the more data you have, and I mean, is that what you're trying to say?
More data. No, I'm not talking about the data. I'm talking about n defines what the technique is. So, right, it's the number of steps you're using. In all these cases, the same number of data, the same amount of data is being used. So by better, I mean that it converges to a lower error with the same amount of data. Or, it's how well the technique makes use of the available data.
Technique, you're referring to the model, or you're referring to
technique? In this case, the technique is which n we're using. So n equals, whatever the n is, it affects, which G estimate we're using. Yeah, I mean, the n step return, right? This is a family of techniques from 1 to infinity. But yeah, they're all subsumed by this in this algorithm, right? This pseudocode. But the parameter is n. As n changes, it just affects, how this estimate is being computed. Okay, well, we can, I guess, move on to the control problem, just like in the previous chapters. We go from the estimation problem to SARSA, or again, the SARSA acronym refers to the state, action, reward, state, action, because that's sort of the chain of information that we're going to use. And here, again, another change is that instead of computing V, we're computing the state action value estimate. And this is the same as in the previous two chapters. We always do this because it is trivial to find the optimal policy given the Q function, whereas given the value function, the state value function, we actually can't just immediately see what the optimal policy is because we don't know necessarily what all the transitions are, right, in the environment. If we have this, we can always compute the greedy policy with respect to Q, QSA, because we know the relative value of every action in this case. So just like before, it's a very simple extension to go from the estimation problem to the prediction problem. And we're just going to use the same estimate for the return, the n-step return. And then we're going to use that to update the Q value estimate here, where we have, again, like the n-step target. And then, as we're training, the policy we're going to follow in the case of just basic n-step SARSA is the epsilon greedy policy with respect to Q, just like before. So this is exactly the same as SARSA from before, except this G now, instead of being the one-step reward, in this case, there's still this G value here includes whatever bootstrapping we are doing. So before in the one-step case, right, this would reduce to this R of t plus 1 plus the Q estimate at t plus 1. Yeah, Whereas now in general, we could have, different values of n. And if n is set to infinity, then we're back to, the Monte Carlo control that we had from chapter 5. Now, you can also, do this just like we had expected sarsa before. You can do the n-step expected sarsa where you sample the rewards. And then when you do the bootstrap part, instead of bootstrapping off the value, the state action pair at this time step t plus n, you instead compute the expected value directly using the policy at the time. So we'll show that more explicitly later, but this is the pseudocode for the n-step sarsa. So we go through the episode, we at every step compute g based on whatever n is. And then we update the q values. And then before we take the next action, we update the policy to be epsilon greedy with respect to the q function. And it has to be epsilon greedy instead of greedy because we still have to guarantee that we explore all the state action pairs. So this diagram sort of shows for a simple grid world example where you start here and the goal is here. And this is an example path taken from some kind of random policy. It's not, I mean, this clearly isn't a random policy, but it's a policy which is not completely optimized yet. And if we're doing one-step sarsa, then the only value that gets updated is the value is for the state action pair that immediately preceded reaching the goal. And the larger n is, the more state action pair estimates are updated along the trajectory. So I have it here, this example. Now, so this is a real example of initializing this with just a completely random policy. So this is showing the path taken when this problem was started with a random policy. You can see it just bounces all over the place and eventually reaches the goal. And here it's showing, so this is showing the value estimates after a single episode, depending on the technique being used. You can see that for one-step sarsa, only this value was updated, right? The value right before the goal. And for 10-step sarsa, all of these values were updated. And then if you go to the extreme Monte Carlo case, I mean, this 1,000, I don't know if this was exactly 1,000 steps, but if this n exceeds the number of steps in the path, then in general, every value along the path will be updated. This grid world example differs from the one in the previous chapter in that now there's just a single reward at the goal. Remember earlier we had a grid world example where there was a reward of -1 for every step. So in that case, you actually get feedback every step, and even, TD0, the values along the path would be updated. So this only applies to a problem where the rewards are very sparse. So there's only a reward at the goal. And for this to learn properly with sarsa, this would have to use discounting as well, because if we have a reward of 1 at the goal, we have to apply this discounting to encourage the agent to get to the goal quickly. Because otherwise there's no advantage to getting to the goal quickly if there's no discounting. You get a reward of 1 regardless. So does everyone understand this figure? How, more state values get updated, the larger n is after, a single trajectory. But it's just showing the practical, the actual practical value updates that are equivalent to this diagram here, where you see just, the 10 most recent state action pairs visited will be affected by this method. For the expected n-step sarsa I mentioned before, this end, which previously was the Q estimate for the state action pair at the step t plus n, is replaced with this V bar, which is computed using the policy. So here, regardless of whatever action was selected at this step, we can average over all of the actions using the probabilities in the policy, and we can get a value which, you know, the sampled value we had, its expected value is this value anyway, but here we're replacing it with the expected value, just like in the case of expected sarsa. So that's the only difference here, and I believe, do I show it here? So here I am, this is showing for this simple grid world, the number of steps during training. So for this example, the optimal policy would just take, you know, whatever it is, like 4 or 5 steps in a straight line to the goal. So lower is better. This is showing very early in the training process, so it hasn't converged. But for this problem, it appears that expected sarsa at, you can change here the learning rate, but at a variety of learning rates, expected sarsa seems to converge faster. In this case, it's n equals 2 seems to be optimal, at least for the first 10 episodes. So just like before, expected sarsa reduces the variance of the updates and should have some advantage in certain problems, which it appears to here. So are there any questions about sarsa, n-step sarsa, or expected sarsa? Is the next section deals with the off policy case, just like before when we were dealing with, you know, both of the previous Monte Carlo and TD learning. We first considered regular on policy learning with the epsilon greedy policy, and then we move on to off policy learning, where there's a behavior policy and a target policy. So in this case, the behavior policy is any policy that has a non-zero probability of taking an action, any action from any state, because the behavior policy has to have full coverage of the target policy. You could see that from this definition. We're going to end up using the importance sampling again to adjust the returns we sample so that they have the correct expected value. But you can see that if at any point the behavior policy has a 0 probability of selecting an action, then this is going to be blow up. This is going to diverge because we can't have a 0 in the denominator. So it's very important that the behavior policy has a non-zero probability of every action. The target policy could be anything. And it's really exactly the same as before with the, I mean, here we're going to start out again with estimating the values rather than learning. So for the value estimates, we have some target policy which we would like to learn the value estimates for, and we're observing samples from a behavior policy. And here the behavior policy, like I said, it has to have a non-zero probability for every state action pair. And we're still going to use this return, the n-step return, just like before. Everything's exactly the same. The only difference is now there's this importance sampling ratio. And the importance sampling ratio also is computed for the same n-step horizon as the return. Okay, so we're basically computing the probability of this particular n-step portion of the trajectory, and we have to adjust the sampled estimate by that ratio. So the book, I mean, it just mentions this. It doesn't actually implement it or show any examples, but I do have an example here. So here they show the pseudocode for estimating. Oh, actually, they go straight to SARSA, right? N-step SARSA. Yeah, so here I also have the algorithm for estimating the state values using off-policy n-step learning. And here's an example on the very simple, actually I should change this title. So this is again the simple grid world where I have defined the optimal policy already, which is just going to the right. So the optimal policy is this. This is showing the trajectory of a random policy here. And this is showing the value estimates after training. This is with one step, but I can make this go up. So as I change this, and you can see at some point the values are wrong here. Like if I go to n equals 4, there's some divergent. Actually, yeah, like this is a value of 200, which means I probably have to lower the learning rate here. But here, if n is sufficiently small, these all are converging to 1, which is the correct value estimate for this problem, right? Because any step along this trajectory, along this line, should have a value estimate of 1 because it will reach the goal. And all these other states won't actually reach the goal because it's just going to go to the right and stay forever, so they'll never have a reward. So this is just showing that even though I'm sampling from this random policy, it can correctly compute the values for the optimal policy. So that's for the estimation case. And then for the SARSA case, this is also showing, so if we do one-step learning, you can see both SARSA and the off-policy SARSA are able to learn this optimal. I mean, it's a very simple problem, right? Like the optimal path is just going to the right. But if I make the number of, and this is training for 1,000 episodes, but you can see that off-policy SARSA, is also able to learn this optimal policy. And in this case, the off-policy SARSA, the behavior policy is just random the whole time. So it's just following the random policy. You don't necessarily have to do this. The behavior policy could be something different, like it could be the epsilon greedy policy. But the random policy is a very simple way to meet the requirements of this, which is that there's a non-zero probability for everything. So for this particular problem, the optimal n is actually pretty low. So as I increase it, sometimes there's problems. Like here, SARSA has learned this, path, which isn't quite optimal. Whereas off policy, in this case, actually is still learning the optimal path, even at n equals 3. Now, remember the other advantage we had talked about previously with off policy learning is that with SARSA, you only have a single policy you're using, and that policy has to have coverage, you know, it has to have it has to meet the exploration requirement. So here I've created this cliff world again. Like in chapter 6, there was a cliff world. So here, this is a cliff world example where there's the same, the start and the goal. And the C squares here represent the cliff states. So if the agent steps onto the cliff, then it gets reset to the starting point and gets a reward of -100, just like in the previous example. So this is showing the solution learned with 3-step Sarsa. And you could see that it is stepping around these cliffs. And it kind of has to, because remember that Sarsa has to follow the epsilon greedy policy. And actually here, am I showing the, hold on. I want to make sure when I'm, yeah, so this is actually, so after Sarsa has finished running, here I'm computing the greedy policy with respect to the value function. So it's not actually using the epsilon greedy policy anymore. But because of the way the training worked, it can't actually learn the true optimal policy because the value estimates it has are for the epsilon greedy policy. And because there's a non-zero epsilon, if it takes this path shown here, there's some probability of hitting the cliff because of the random steps. And that's very costly. So the policy it has learned is to sidestep the cliffs and get to the goal from around this, you know, more indirect path. Whereas the off policy learning, because I'm just following the random policy, it is actually learning the optimal policy, not the optimal epsilon greedy policy, because the target policy no longer needs to have this property where it explores the environment. So this is, again, the same analogous to the cliff world thing in the previous chapter. But this is one example of why a case where off-policy learning can have an advantage, is when you have a situation where really there's a substantial difference between what policy is optimal in the case where you have some random behavior. So, are any questions about this example?
So let's see, for the source path, essentially the straight path, because all the C's are basically cliffs. Oh, wait, never mind. Yeah, I answered that myself. All right. That
Okay.
makes sense, you know, between you know the source path because of epsilon greedy policy usually that there's a high risk of basically falling off a cliff, while you know having an off policy helps with mitigation of that, given that there's a policy and a different policy that's being evaluated from.
Yeah, so this is just extending what we had before, and this is similar to like with Q learning. Well, I mean, this isn't exactly Q learning, although in general, even off policy, expected Sarsa can be, Q learning is a subset of that. But yeah, this is not expected Sarsa here yet, but yeah, this is just showing that, yeah, following a completely random policy, at least in this example, you can still learn this optimal path. Let's see. So this section, I don't know if, I mean, yeah, this is an alternative way of computing the correct. So this G is supposed to be an estimate of the discounted return for the target policy, not the behavior policy. So we use the importance sampling ratio if, in fact, these rewards are being collected from a different policy, behavior policy. We use this importance sampling ratio to correct this, so that now if we multiply this by the importance sampling ratio, we end up getting an expected value that is correct for the target policy. Here, there is this alternative calculation of G where we are using the importance sampling ratio here. So like normally it would just be this for this return, but, or yeah, I believe so. But then it's being averaged with this other the value estimate at the current state. So this method, which they're calling here control variates, ends up reducing the variance of the estimates, because normally when you use the importance sampling ratio, there are a bunch of values that where the ratio is very large, right? And those are like underrepresented trajectories when this value is large. And then there are trajectories which never occur under the target policy. And those are all set at 0. So those are completely ignored. And what's happening here with the control variates is we're taking the case where rho is 0. And in that case, we're going to use the value estimate we already have instead of setting it to 0. And what's compensated now is that if rho is 1 instead of 0, if rho is 1, it just means that this trajectory is identical to what we would expect under the target policy. And in that case, we just have the usual value of the return. And then if rho is much larger than 1, we end up having these underrepresented trajectories that we are multiplying by a factor to compensate for that, right? But then we're also going to be subtracting the existing value, right? If rho is greater than 1, then this correction term becomes negative. But the point is that this expected value is the same as the expected value if we just do the importance sampling in the traditional way, where we just put the rho in front here. But using the existing value estimate reduces the variance. And the simplest way to see that it reduces the variance is in the extreme case where rho is either 0 or 1. I mean, if rho is 1, it doesn't matter, it's the same. It's really where if rho is 0, we're not just throwing out all that information. We're going to sort of use the existing value estimate, which makes sense, right? If rho is 0, it just means that we observed a trajectory that is not useful for the target policy, right? Or at some point in the future. So this is just saying, if that's the case, we might as well, still use the value estimate that we have. And then, but the specific form of this ends up keeping the expected value the same. So you can, so here I have this implemented, this value estimates using control variates. Here's the line where it computes G, and you have to use the importance sampling ratio. But in order to see that this actually does, in fact, reduce the variance. So here's an example of the same exact problem, right? Just showing that you have the random policy, then you have the optimal policy. And this is showing that the value estimates are correct in this case, even though we're doing off-policy learning. Now, let's see. I have this example here. Okay, so this is showing this exact problem where we know that the correct value estimates are 1 right along this path. Now I'm showing a case here where all the settings are, this is all set up where the value estimates are all correct, right? So this is like 0 error on this case. Here, I am showing the error with the number of episodes at a particular value of alpha and n. So after about 20 episodes, a little more, both of these methods have converged. And yeah, actually, if n equals 1, I think, is there a difference in these methods? So if n equals 1, then this is h of t plus 1. I guess that there should still be a small difference in the methods, which reduces variance. But in this problem, there's not much of a difference. Where you really start to see the difference is when you increase n. Now, in this particular case, in this simple grid world, n equals 1 may already be like the optimal value of n. But in other problems, a higher n might be better. And in this case, if you set n equals 2, and you change the learning rate, like if I make the learning rate too high, which is a classic case of things not converging, you could see that this orange line represents the error in value estimates using the control variate formula. You could see that initially it's way off and it gets screwed up. But after a certain number of episodes, it does converge. The case that doesn't use control variates, this starts diverging, and you could see even after 30 episodes, it hasn't started to converge again. So this is at least one demonstration of this method lowering the variance of the off policy estimates. And you can see if I go up to n equals 3, the problem gets worse. I mean, eventually, like this learning rate is way too high probably for n equals 5, but you can see that the control variate method actually is still converging. So this is just a better way of, yeah, if I go out here, you could see this, the method without control variates is completely diverging the error where the learning rates are. And that's because, you know, as n gets larger, this importance sampling ratio here, or actually this should be, yeah, so like this is a recursive formula, right? But these are going to get multiplied together, right? Because this g depends on the g at one time step into the future. So if you were to write this out explicitly, you would have a series of these ratios. And like, let's say one of these ratios is like 10 and another is like 10. This is going to very quickly blow up to very large values. And this is what happens with off-policy learning is, in general, you have these very large importance sampling ratios that have to be averaged out with all the zeros in order to get a correct value estimate. And here, because of this term, all of those very large values, like, so the values that would be 0 are now non-zero, and then the very large values are smaller because of this correction term. So the variance is lower, and the convergence will be better, and also will be less sensitive to the learning rate, which is good. And I think we had, what, in the previous chapter, there was some other method of reducing the variance on for off-policy learning, but now I don't recall exactly what that was. Oh yeah, it was the weighted importance sampling as opposed to, but yeah, so this is just for the n step return, this is just a recommended way to reduce variance. Okay, so finally in this chapter, for sort of the full generalization of Q learning, which we haven't really had yet, we have to do something a little different from before because now there's like multiple steps. Remember in Q learning, we just have this single step into the future and we take the maximization. Whereas for n-step methods, we have this, n-step trajectory. So we can't exactly consider, we can't ignore what happens on the trajectory. Like in Q-learning, for the value update, we take the maximization over the actions at the transition state. But here we have this trajectory, and in the tree backup algorithm, how it works is that we consider both. So we consider the actual samples and returns that we get along the trajectory, but we also consider the value estimates for all the actions that were not taken. And the two are averaged together in this manner where we have the reward so here it's showing the n-step formula, but so we have the return observed for this one step, and then we have the explicit calculation of the expected value of the next state, which is taken for every action other than the action that was taken, which is a of t plus 1. So for all the actions that weren't taken, we're using the existing estimates. And then for the action that is taken, we actually look at the return that we get into the future. So it's why it's called this tree backup, because even though this is branching, we only have one trajectory that we're considering for the rewards, but we're still able to account for the branches using the existing estimates. And this algorithm, in general, can also be an off-policy algorithm, because regardless of whatever the trajectory we take is, when we compute this branching, we're using the target policy to compute the value estimate. So just like with off-policy learning, it doesn't really matter what the behavior policy is, because whatever action is taken, we are just replacing what would have been our estimate at this step with the data we get from the action that was taken. And then for the actions that weren't taken, we're actually using the target policy estimate. So that's why this technique is sort of a way of doing off-policy learning without the importance sampling ratio. And if you recall back to Q-learning, that was the same thing. But with Q-learning, we have some behavior policy, right, which in most cases is like could be the epsilon greedy policy. And then we're considering the target policy as the greedy policy, but we don't actually have to use the importance sampling ratio because we are explicitly computing this estimate using the target policy. So it's sort of like similar to expected SARSA, where we're computing the expected value. So, I also applied, so this is using the tree. This is showing again, like on the simple grid world again, how this tree backup, I mean, this is showing for n equals 2 or higher, but this is also able, depending on what the learning rate is, this seems to be able to converge. If the learning rate's too high, it won't work, but well, maybe, yeah. So even I think with n equals 5, even like SARSA has a lot of can have trouble with this task. And it's also only over 10 episodes of learning, but this is just showing how the tree backup algorithm can solve the problem. In this case, it's also using the random policy for this. So the behavior policy here is totally random, and yeah. The final section of this chapter is what they're calling this Q sigma learning. And what this technique does is it sort of subsumes all the previous techniques other than SARSA, because SARSA is explicitly on policy. This is still an off policy technique. Although if you set the target and behavior policy to both be epsilon greedy, this is also can be equivalent to SARSA. So in this case, this factor of sigma can control on a per step basis whether you do the SARSA style update or you do the tree backup update, where you're considering all the branches. And if sigma is 0, then this technique is equivalent to the tree backup technique. And if sigma is 1, then it's equivalent to SARSA or to off policy SARSA, because notice that for this pseudocode, we do have to compute the importance sampling ratio, which we do use in expected SARSA. Although it ends up being equivalent to expected SARSA with control variates, the way the update works. If you look at the formula, it does have that added stability benefit. So this technique, depending on what you choose for sigma and how you set up the behavior and target policy, this can sort of subsume all of the previous techniques in this chapter. And for different problems, there could be, you can sort of explore the advantages or disadvantages of all the values of n, learning rates, etc. This is showing Q sigma. I think by default, I just have it pick a value of sigma that's 0.5. Like if you just want to sort of split the difference between everything. If you pick sigma is equal to 0.5 at every step, it's just averaging on both of the techniques together at every step. So anyway, this is showing, again, this technique working in the off policy setting with this cliff world, where the optimal path goes straight. But, and depending on the settings, like this may also find, like, notice like this solution is a little bit in between, where it is hugging the cliff somewhat, but it's not exactly going the optimal path. Whereas again, this is doing it with n-step SARSA, which is not off policy, where the only thing it really learns is a path which really takes a wide path around the cliffs. And that's just, again, the difference in this case between the on and off policy learning. And this, if you make tweaks to this, like sometimes it does learn the optimal path. But I did make this other example as well to show why sometimes like you really do need off policy learning. So in this case, I've set up this cliff world where now the cliffs are set up such that there is no path to the goal that you can take that goes all the way around the cliff. Like you have to go straight through. There's no roundabout path. And I've also added a secondary goal up here. So directly north of the start, there is a way out, which doesn't give any reward. It gives a reward of 0, or I could set it to a negative value as well. So the optimal path is the same. It's just going right, and it would give you a reward of 1 for exiting. But if you try to do this with n-step SARSA, like any number of n, it doesn't. Well, first of all, if it has to follow the epsilon greedy policy, what it's doing here, probably the optimal policy in this case truly is to exit here, because the probability of falling off the cliff with a negative reward makes it where you would never take this path. But the policy you really want to learn here is getting to the goal, and this is sort of a distraction exit here, which the on policy technique will always get stuck in. Whereas, here, it's actually able to learn it. And now if I change this so that the exit is even worse, so like if the secondary exit here, let's say it's a reward of like -10 instead of 0. So then it's like actually bad, like depending on the value of epsilon, it may at this point actually be beneficial to go to the goal, even with the epsilon greedy policy. But it may be very difficult to learn that. Whereas let's see if, so in this case, even though I change this to -10, this Q sigma with the parameters I've chosen is still able to find that it's better to go to the goal. Whereas now n-step source is going to get really confused because the goal it was reaching now has a negative reward, which is undesirable. But also if it tries to step to the goal through here and it's following epsilon greedy and it falls off a cliff, it has a negative reward. We could see that now this is running and it's really having trouble converging to anything. Probably these episodes are taking a very long time and it's getting stuck. And I would have to set the value of epsilon probably higher for this to not fail. So you can set up these problems where on policy learning like this will fail. Now, in this case, because this technique's pretty flexible, the behavior policy I'm using is not the random policy anymore. I'm actually just using the epsilon greedy policy with a larger value of epsilon to encourage exploration. So this will also speed up learning because if we use the totally random policy, the episodes will be slower than if we use a policy which is getting closer to optimal as we train. So this would be the closest thing to Q learning where we're trying to estimate the optimal policy and we are following the epsilon greedy policy, which for certain problems would be sort of the best of both worlds. So you could see here, like the way I set this up, n-step source I didn't even find, like this is just getting stuck and it's not reaching any of the goals. So, this is at least one demonstration problem where you really do need, you probably need off policy learning to even have a technique converge. Because here, like you might say in this other problem, well, the on policy technique, it's still found a solution. It's just a more conservative solution. So that could be fine in some cases. This won't be able to learn the true optimal, but it can find, a conservative version of the optimal policy. But if the problem is set up like in this way, whatever, even if I change the value of n or something, like you could play around with the parameters here and make the learning rate smaller, but it's just not going to be able to converge to any policy because it's sort of a pathological case. Whereas with this technique, it is able to find it. Oh, I just said, actually, oh, interesting, with n equals 5 and setting the learning rate lower. Okay, so this actually was able, I'm surprised it was able to converge. Okay, but if I set this, maybe if I set this to -1, if I make this back to 0, it's likely, or -1, it's likely that it will find the secondary goal and prefer that. Yeah, okay, well, this is getting stuck now. I believe this technique is more stable. Although I say that, I think if I set, for some reason, in this really small grid world, it seems like an n of 1 is still the most favorable. But if I made the problem larger, probably a larger value of n would benefit. Well, yeah. I mean, now at this point with this technique, there are a lot of parameters to play with. And, you know, in the book, they don't even really show an example of this on a different problem, probably because it's just, at this point, there's so many different types of problems that would benefit from different parameters in this technique that it's hard to have any sort of general rule for that. But here, I at least tried to make some pathological examples here. I think this is probably the best demonstration of just having what is this? Okay, I'm not sure what this one of where you know, the off-policy learning is able to find the optimal even when you have these obstacles in the way. So yeah, I mean, there's not really, again, like I wouldn't worry too much about the details in this chapter. It's more just like understanding conceptually which types of problems benefit from n-step methods and how you can sort of think of all of the methods as being some version of this algorithm where you adjust the value of sigma and how the target and behavior policies are updated. Yeah, I mean, with this technique also, you even have the ability to choose how the behavior policy is updated. So yeah, there's a lot of flexibility in the technique, but it also means there's a lot of things you have to check for a particular type of problem. So are there any remaining questions on this or the these sort of cliff examples I came up with? These examples are just sort of inspired by this cliff world example from chapter 6, but where, remember in chapter 6, it was showing how Q learning, even though during training it falls off the cliff more, it's able to learn the optimal path that hugs the cliff very closely. Okay, well, yeah, the next chapter is a lot of pretty substantially different stuff from what we've been looking at so far, and it concludes part 1, so should be interesting. Yeah, and there's some interesting examples, so I guess, yeah, we can move on to chapter 8 next time. And yeah, if there's no further questions, then we can be done.
Thank you, Jason. See you next time.
Yeah, sure. Sounds good. Thanks everyone for coming, and yeah, see you next time.